All right, this tape lecture is going to be on concepts of enthalpy and also looking at what's called heat of formations and how we can use them to calculate the enthalpy of any reaction. Okay, again, enthalpy, delta H is enthalpy, is defined as heat per mole. So delta H is what we deem enthalpy, and again, it's impossible to really measure the total enthalpy of something. What we have to do is figure out the change in enthalpy. And that's why we see the triangle there in front of the H. How much enthalpy is either increased or decreased of the system or the reaction, and we can measure that based on changes in temperature, as we've seen in last example in the last lecture, and also the last set of problems. So if we know the heat Q, the heat that is either liberated or absorbed by a reaction, and dividing it by the number of moles that is reacting, that'll give us the enthalpy of the reaction per mole of that material. Now, a couple of concepts of enthalpy. It is dependent upon the direction of the reaction. So here you see the reaction, A plus B producing C. This reaction has an enthalpy of positive 12 kilojoules per mole. Now, first of all, based on that number, is this reaction endothermic or exothermic? Hopefully you said endothermic. Endothermic reactions have positive delta H values and Q values. So this is endothermic. Energy is coming into the reaction so that this reaction can proceed. Okay, so that energy comes from the surroundings. Now, what happens to the enthalpy if we flip the reaction? What happens if we have the reaction C going to decompose to produce A and B? What do you expect the enthalpy of this reaction to be? Hopefully, you said negative 12 kilojoules per mole. Flipping the reaction, now it becomes exothermic. So the direction of the reaction is very important. When you flip a chemical reaction, the sign of the enthalpy changes. Also the heat value, the Q value as well. It is state dependent. So we look at this reaction, 2 molecules of hydrogen gas, 1 molecule of oxygen gas produces 2 molecules of liquid water. Key thing, liquid water. The enthalpy for this reaction is negative 571.6 kilojoules per mole. Okay, so this reaction is exothermic. It has a negative delta H value. Okay, now this same reaction, but instead of producing liquid water, producing gaseous water, the enthalpy of the reaction, and I looked it up before I started this lecture, was negative 483.6 kilojoules per mole. Okay, why is there a difference? Well, it's because the water is in a different state. And for liquid water to become gaseous water, as we saw back a couple lectures ago, to convert liquid water into gaseous water, we have to break IMFs, and that is an endothermic process. Energy has to come in to break it. And because more energy goes into breaking the liquid water into gaseous water, some of the energy of the reaction is going to go into the phase change of the material. And therefore, the amount of heat that is released is less because some of it went into changing the water to its gaseous state. So the state is very important. So when you look up these numbers as we get into the next set of problems, you must make sure that the sign of the state of the material is included and that you pick the right state of matter for it, because it will differ between solid, liquid, and gas. Okay? Enthalpy is an extensive property, which means it depends upon the amount of material that is reacted. So if A plus B produces C, if we have 20 kilojoules per mole of this reaction, how it is written, 20 kilojoules is absorbed, it's positive, it's an endothermic process. 20 kilojoules of energy is needed for every mole of this reaction to occur. Now, if I triple the mole quantities, instead of reacting 1 mole of each, if I react 3 moles of each, the amount of enthalpy that will be released, or I should say in this case absorbed, will be positive 60 kilojoules per mole of reaction. And you'll typically see this concept of per mole of reaction, which means how the reaction is written, that's how much heat is liberated. Now, 20 kilojoules of energy is released per 1 mole of A. In the second reaction, 60 kilojoules is absorbed, I should say absorbed, not released, per 3 moles of A. If I divide both of those down, specifically the last one, I still get 20 kilojoules per 1 mole of A. So I'm still getting the same amount of heat that's produced per mole of material. Okay? Per 1 mole of that material, the number is never going to change. But if I double the quantity of something, I'm going to double the heat produced or absorbed by the reaction. Okay? So just be aware of that. It is dependent upon the number. And if you double a reaction, you're going to double the amount of enthalpy that is released for that reaction, how it is written. Okay, lastly, if I have a thermochemical equation like this one, okay, the enthalpy of this reaction, okay, is negative 184 kilojoules per mole of reaction. So how the reaction is written, if I react 1 mole of silicon dioxide, 4 moles of HF, I'm going to produce 1 mole of SiF4 and 2 moles of water. How this reaction is written, I'm going to produce negative 184 kilojoules of energy based on reacting 1 mole of SiO2 to 4 moles of HF. What would be the enthalpy of the reaction per mole of HF? Keyword per mole of HF. Well, this reaction is producing 184 kilojoules, but in the mole of the reaction, I'm producing, or I'm saying I'm requiring 4 moles of HF. So if I want to get this thermochemical equation in terms of HF, I would have to divide it by the coefficient to get it per mole, per every 1 mole of HF. So if I take my calculator out, negative 184 divided by 4, and I get negative 46 kilojoules per mole of HF. So if I were to react 1 mole of HF, this is how much heat would be liberated for 1 mole of it. 4 moles of it will produce release 184 kilojoules of energy. Okay? What I've essentially done here in B is taken the reaction and literally cut it in fourths. 1/4, 4 divided by 4, 1 divided by 4, and 2 divided by 4. If I cut the reaction by a quarter, I cut the enthalpy of the reaction by a quarter. And now we would see the reaction as negative 46 kilojoules per mole of reaction. How this reaction is now written, this is how much heat would be liberated if we reacted a quarter of a mole to 1 mole of HF. Okay? What would be the enthalpy of reaction per mole of H2O? Production of H2O. Okay? So go ahead real quickly, look at the numbers. What should that answer now be? Again, how the reaction is written, it's negative 184 kilojoules, but that is for the production of 2 moles. If we want to produce only 1 mole of water, we need to divide it by the coefficient that's in front of the 2, in front of the water, which is a 2. And dividing that, we now get negative 92 kilojoules per mole of H2O. So for every mole of water that is produced by this reaction, we are going to release 92 kilojoules of energy. Okay? In essence, again, like we saw with B, we've literally taken the reaction in A and we've cut it in half. So we've divided all the coefficients by 2 because, again, enthalpy is an extensive property. And therefore now the reaction, because we are producing 1 mole of water, this reaction, how it is written, would have an enthalpy of negative 92 kilojoules per mole of reaction. Okay, so enthalpy is extensive, and if you want to take the reaction, usually the enthalpy is how the chemical reaction is shown and displayed, but if they want it per a specific material, you will have to divide it by the coefficient that's in front of that material to get it per mole of that reactant or product. Okay? All right, let's turn the page. The second concept in this lecture is something called enthalpy of formation. Enthalpy formation is the amount of heat either released or absorbed by producing or making 1 mole of substance from its elements at their standard states. Okay? Standard states would mean the reaction is occurring at 1 atmosphere of pressure, which is typically atmospheric pressure on a normal sunny day here in Wisconsin, and the temperature would be a little bit warmer than room temperature, 25 degrees Celsius. Normal room temperature is about 20 degrees Celsius. So a little bit warmer than room temperature, probably around 80 degrees Fahrenheit or so. These are considered standard state conditions. Okay? So it's the amount of heat produced or absorbed to make 1 mole of something from its elements in their standard states. So at these conditions, what is the state of matter? Now, when you come into class in my AP chemistry classroom, for those of you that do, I have that periodic table that's in my large periodic table in the corner of my room. The color of the elements tells you what state of matter the substances are. The elements that are black, for those of you that have seen that periodic table, that means in standard conditions they are solids. If it's blue, they're liquids, and if they're red, they're gases. Okay? So, looking down here, the key thing with standard states of enthalpy is the standard state of an element, okay, is what state of matter it exists in. Carbon solid, for example, has multiple different solid states of carbon. These are called allotropes. The two basic types of carbon solid is we can have graphite carbon, okay, which is what you find in pencil lead, and then you can also have carbon in its larger, more compressed state, which is diamond. Again, a diamond is nothing more than compressed carbon at enormous temperatures and pressures. Both a diamond and your pencil lead both are composed of carbon atoms solely. Okay? They are just different solid states of carbon. Now, the most common state of carbon is graphite carbon. This is underneath normal temperature and pressure conditions. If we exasperate that and increase the pressure enormously in the temperature, we can now make it into diamond. So when we look up these numerical values for their enthalpies of these different substances, you need to pick the state of the material that is its most common state. And you'll know that because when you look it up on the tables that I've given you in Canvas, the most common state will have an enthalpy value that is 0. Elements that are in their standard states have an enthalpy of substance that is 0. Any element in their normal standard states will have an enthalpy of 0 by definition. Most other chemical compounds and ions will have a value that's not 0 because those are not standard state conditions of the materials. Okay? All right, so here's an example of an enthalpy of formation problem. Key thing to have it, we're going to make 1 mole of it, so you need to have a 1 in front of the chemical compound. 1 mole of ethanol, this is the chemical compound ethanol, contains 2 atoms of carbon. So we need to have 2 atoms of carbon, and you'll notice it's in its graphite state because it's its most common state at standard state conditions. There are 6 hydrogen atoms, so we need to have hydrogen in its most common state is H2. Hydrogen exists in its standard state as H2 gas. We need 3 of them because we need 6 hydrogen atoms. And then there's only 1 oxygen atom. The standard state for oxygen is O2 gas. Okay, again, you have to know the 7 diatomic elements. And again, the 7 diatomic elements, think of Hofbrinkel, hydrogen, oxygen, fluorine, bromine, iodine, nitrogen, chlorine. These 7 elements, their standard states are diatomic states. Therefore, we need to actually have a 1/2 in front of the oxygen because 1/2 of 2 gives me 1. It is okay to have fractions in thermochemical equations as we saw on the previous page because of the requirement that we make 1 mole of the material. In order to make 1 mole of it, okay, we must then utilize fractions potentially on the reactant side. Now, by definition, the enthalpy of all these elements is 0 because they're standard states. So the enthalpy of this reaction is equal to the enthalpy of formation of the compound because it's the only chemical compound in the table that has any enthalpy values for it. So we now know the enthalpy of this reaction and also the enthalpy of this material, okay, that it has at 1 atmosphere and 298 K. Okay? All right, real quickly, write a thermochemical equation for the standard formation of C2OH2 acetylene, whose enthalpy is positive 226.7 kilojoules per mole. All right, write a reaction just like the example above. All right, we have to make 1 mole of C2H2. Okay, so we need carbon. What's its most common state at 1 atmosphere and atmospheric conditions? Graphite. We would need graphite carbon in its solid state and hydrogen gas. Hydrogen in its elemental state is H2, and it's a gas at 1 atmosphere and 298 K. All right, we have 2 hydrogen atoms on both sides. All I need is a 2 in front of the carbon, and right there is the thermochemical equation for the production of acetylene from its elements. And again, we make 1 mole of it. the enthalpy of formation for this substance, looking up C2H2 on my table, which is exactly what I told you it was. Okay? So the enthalpy for this reaction would be 226.7 kilojoules per mole. It is also the enthalpy of formation, which is given by a little F subscript. The enthalpy of formation of acetylene is also 226.7 kilojoules per mole. So because of the definition of this reaction, this is both the enthalpy of the reaction, but it's also the enthalpy of forming this chemical compound from its elements. Now, why are we learning about enthalpy of formations? Because it makes or creates this equation on the green sheet, which is very easy mathematically, and that is we can calculate the enthalpy of any reaction at its standard states. Now, whenever you see me put this little zero symbol to the upper right of it, that means standard state conditions. So whenever we are in standard state conditions, we can calculate the enthalpy of any reaction by using enthalpy of formation values. And you can see this equation is on the green sheet. I have to first summate the heats of formation of all the products, looking up the enthalpy values on that table that I just showed you, then look up all the enthalpy of formations of the reactants and summate all of them together. And when I subtract them, the summation of the products from the summation of the reactants, the difference in those enthalpies will give me the enthalpy of the reaction. We can use these tables of formation values to calculate the enthalpy of any thermochemical equation. All right, so let's go ahead and do an example of that. So we have 2 aluminum solid reacting with iron 2 oxide, producing aluminum oxide and 2 irons. Okay, if I look up the heats of formations of all these substances, okay, iron 2 oxide, so this is the table that I'll look up. Okay, and again, these are all kilojoules per mole. I won't keep writing that because that's the label on it. Aluminum oxide, looking it up on that table, is negative 1,675.7. The enthalpy of formation of aluminum, when you look up just Al solid, is 0. Why is that? That's because it's an element in its normal state. Aluminum solid, it's not a diatomic element, it's not Hofbrinkel. So aluminum solid is its standard state conditions, and by definition, any element in its standard state conditions has a 0 enthalpy. The same is true for the iron. The iron, when you look it up, is also got a 0 value. So any element in their standard states, when you look them up on these tables, their delta H value will be 0. Okay? So now I'm going to summate the enthalpy of all of the products first. That is the biggest thing to remember. The products need to be summated first. So there's a 2 in front of the iron. You have to make sure that if there is a number out in front of it, you magnify the enthalpy, because the enthalpy in the table is for 1 mole. And we saw from the previous page that if you have more than 1, you have to apply that coefficient. So 2 times 0, this is the iron, okay? Plus, there's 1 aluminum oxide. The aluminum oxide has a value of negative 1,675.7. We'll summate that all together, and we get negative 1,675.7. All right. The reactants will then summate. The aluminum has a 2 in front of it. 2 times 0 is 0 because it's an element. And we have 1 iron oxide, which is negative 824.2. So summating that, we get negative 824.2. So we have negative 1,675.7 minus, it's a subtraction, a negative 824.2. Subtracting a negative means we make them positive. So negative 1675.7 plus 824.2. We get an enthalpy of reaction that's negative 851.5 kilojoules per mole of reaction. So the enthalpy of this thermochemical equation is now been calculated. I know the enthalpy of the reaction because I can simply summate the reactants and the products, summate the products, summate the reactants, subtract products from reactants, and I can use those table values to calculate the enthalpy of any chemical equation now for this entire unit and moving on forward in this class. It's a very important tool to utilize to figure out the enthalpy, the heat of any thermochemical equation. Because the value is negative, is this an exothermic reaction or endothermic? This reaction is largely exothermic. It has a huge negative value on it. Okay? Now in the page. So in your practice problems, here are some example problems that I'd like you to find the enthalpy of the reactions for. You can pause this lecture right now and then go ahead and go through utilizing the table of values that is found in your Canvas module. Look up thermochemical tables and pull it up and then use those tables. If you want, if you have access to a printer, print it off. It'd be a great thing to print it off. That way you can use these values of these tables, these substances, to be able to calculate the reactions for any of these. So go ahead and do this. Go ahead and try to do number 1. Pause the lecture now. When you restart the lecture, you will see the answers supplied by me, because I'm going to pause it now and do the own work so that I can go through this more quickly for you. All right, so looking up the values, again, we are going to do products first. You have to make sure to look on the green sheets. If you don't remember this, look on the green sheet. It says products first. So the products are the 2 KCl solid and the 3 oxygen gases. So we're going to take 2 times the KCl value on that table plus 3 times the oxygen value minus 2 times the potassium chloride value. So KCl has a value of negative 436.7. Oxygen is 0 because it's an element in its standard state. And then KCl3, potassium chloride, is negative 397.7. The most common thing that students forget to do is they forget to multiply by the coefficients. Enthalpy is extensive. The more you have, the more heat will be produced or absorbed. Okay, be aware of signs. Again, at the end, you're going to have subtracting a negative, and we get a final value of negative 78 kilojoules per mole of reaction. How the reaction is written, the enthalpy of this reaction is negative 78 kilojoules per mole. Okay, so this is the amount of heat released by reacting or decomposing 2 moles of potassium chlorate. Now, if they wanted to know the heat of the reaction per mole of potassium chlorate, then we would have to take negative 78, divide it by 2, and we get negative 39 kilojoules per mole of KCl3. But that would be making this equation not have a 2 there, but have a 1 there. And if I cut it in half, the enthalpy is cut in half. All right, continue on, do the next 2 problems. I'm going to pause the lectures myself, and I will then go through it and put the numbers up there just to check to see how well you are finding the values on the table and using this equation. All right, so if you did the problems correctly, number 2, you should have gotten negative 1,450 kilojoules per mole. And for the third reaction, you should have gotten negative 15.2 kilojoules per mole. So again, in problem 2, you're going to multiply 2 times the carbon dioxide value, 4 times the water value, 2 times the methanol value, and 3 times O2. Be careful with the water. The water value you should have is negative 285.8. Some students plug down negative 241.8, but again, negative 241.8 is the value for gaseous water, not liquid water. Make sure you look at the right substance and the right state of matter. The state of matter is critical because, again, if there's a phase change, the value of the enthalpy does change. Make sure you're looking up the right material and its right state, okay? The only thing that's 0 in the second equation is the oxygen. It's the only element that there is in the reaction in a standard state. All the other substances have numerical values. And again, don't forget about subtracting the negatives, which makes usually the products end up being positive unless they have an endothermic value, which is not all that common. Okay? Subtracting a negative, making it positive, we get the value there. In the second reaction, same thing. Make sure you summate the products first, the reactant second. The only thing that has a coefficient is the hydrogen ions. And again, when you look up hydrogen ions, it has a value of 0. Some of the ions will have a value of 0. Not all of them, but again, there are ions in this table just like there are molecules and other compounds on there as well. Okay, so multiplying, adding, you get a value of negative 15.2. So you have a homework assignment now, which you have some practice problems to do, utilizing the same equation and being able to get extra practice, but you should be able to calculate the enthalpy of any chemical equation by simply looking up the numbers, picking the right state of matters, and making sure to summate products minus reactants. If there is a coefficient in front of them, you must multiply the coefficient by the value in the table, because the value in the table is for 1 mole of it, and if there's more than 1, you have to magnify it by that coefficient. Okay? Pretty simple technique. It should be an easy mathematical problem. Just be aware of your negative signs, be aware of that basic algebra, and don't forget to multiply by the coefficients. All right? Thanks for listening, and we're getting close to the end of the enthalpy unit, so we're almost there. Canvas, I have supplied you a link that has thermochemical equations, and here you'll notice all the different elements and their delta H value. Currently, we are not looking at these other values of S and G. We will when we get into looking at the second part of thermodynamics, but that's not till towards the end of the year. We are looking at the enthalpy of formation values of all these substances. So I want to look up C2H2 on this table. This is alphabetical, and there are two. Find C2H2 right here. The enthalpy for it is 226.7. Iron 2 oxide is negative 824.2 of it. Here's the second page. And again, we are not looking at the S and G for this unit. We're just going to look at the enthalpy values.